Hello everyone, my name is Tsepo and welcome back to Untitled Engineering. Today we are doing another exercise on Otto Power Machines N6, which is an exercise I've taken from my textbook and it reads as follows. An engine working on the constant volume cycle has 4 cylinders and operates on the 4-stroke Otto principle at 3000 revs per minute. The engine has a compression ratio of 8.6:1 and develops an indicated power of 30 kilowatts with an indicated mean effective pressure that is equals to 700 kilopascal. Compression and expansion index N is equals to 1.3. The piston diameter and stroke are equal. The pressure at the beginning of the compression stroke is equals to 90 kilopascal, and the highest pressure in the cycle is equals to 4,400 kilopascal. And then the questions they say, question number 1, calculate the piston diameter in millimeters. Question number 2, calculate the volumes in cubic centimeters at all the main points in the cycle. Question number 3, calculate the pressure after compression P3 and after expansion, which is P4. Question number 4, calculate the work done per cycle. And then question number 5, they say calculate the temperatures at all the main points in the cycle if the temperature at the beginning of compression is 350 kelvins. And this is the information that we are given. We are told that the engine that we are working with, it's a 4-stroke 4-cylinder engine. We are given the rotational frequency, the ratio, the indicated power, the mean effective pressure, the index of polytropic law, and we are told that this piston diameter is equals to the stroke length. They gave us pressure number 1, and then they told us that the highest pressure on the cycle is 4,400. We know by now that the highest pressure will occur at this point, which is point number 3, which is where we are going to place it. And the questions. Question number 1, they say, calculate the piston diameter in millimeters. A, we know the piston diameter, we can get it from the swept volume is equals to pi divided by 4 times dp times the stroke length. We do not have this, therefore this one we are not going to use it for now. We are going to use the formula that's we are going to use the indicated power. Indicated power, we know it's given by PM LANE. This is where we are going to get our piston diameter. We substitute. Indicated power is 30. It's equals to 700. Stroke length, we are told that the stroke length is equals to the piston diameter. We do not have the value of the stroke length. So in place of the stroke length, we are going to put the piston diameter because it is equals to the stroke length. We put the piston diameter so that we only have one unknown on our equation, which is the piston diameter that we are looking for. So instead of putting the stroke length, we are going to say piston diameter times the area, which is pi divided by 4 times the piston diameter squared, times the rotational frequency, which is 3000, divided by 60 to bring it to seconds because it is in revs per minute, and divided by 2 because we are working with a 4-stroke engine, which we know it will take 2 revolutions of the crankshaft to finish those 4 strokes. And then we say the number of cylinders as 4. Now, this is the stroke length. Oh, it's the piston diameter, sorry. We are going to combine these two and we will end up with something like this. And then we simplify this. Piston diameter cubed, it's equals to 30 times 4 times 60 times 2 divided by 700 times pi times 3000 times 4, which will give us, we will say here, which will give us our piston diameter as 0.0817 meters. They said we must calculate the piston diameter in millimeters, therefore we're going to say it is equals to 81.7 millimeters. And then we go to question number B. They say calculate the volumes in cubic centimeters at all the main points in the cycle. They say we must calculate in cubic centimeters. We'll start by calculating the swept volume, which is equals to pi divided by 4 d p squared times stroke length. We know that PV1 is equals to the swept volume plus clearance volume divided by the clearance volume. So first we are going to calculate the swept volume and the clearance volume. We already know that these two are equal, therefore we are going to say pi divided by 4. They said they must calculate in cubic centimeters, so we will just change it. We change the piston diameter here from millimeters to centimeters so that we do not have to convert back to cubic centimeters from cubic millimeters, which will be 8.17 cubed, because this we already know are the same, so it will be like this. And we are going to get our swept volume as 423.308 centimeter cubed. And then from here, the value of our clearance volume, it's equals to 1. The ratio is equals to 1 plus Vs divided by Vc, which will be equals to Vs is equals to R minus 1. And then we're going to get our Vs is equals to 423.308 divided by the ratio, which is 8.6 minus 1. And we are going to get that our value is for Vc, it's equals to 56.356 centimeter cubed. And then from here we know that V3 is equals to V2. It's equals to V3 and V2 are here. They only cover the clearance volume. Therefore, they are equals to the clearance volume, which is equals to 56.356 centimeter cubed. And then V1 and it's equals to V4. It's equals to the clearance volume plus the swept volume, which will be 56.356 plus our swept volume, which is 423.308, and it's equals to 484.664 centimeter cubed. And we are going to put them here. Our V1 and V2, V1 and V4, 664 484.664. Our V2 and V3 is 56.356. And then we are done with question number B. We go to question number C. They say calculate the pressure after compression, which is P2, and after expansion, which is P4. Let's erase this. It's question number C. We are going to use this side, start with P1, P2, sorry, start with P2. We're going to use the information between point 1 and point 2, which will be P1 V1, and it's equals to P2 V2 raised to n. And we are looking for P2, we make it the subject of the formula, which will give us P1 times V1 divided by V2 raised to n. We already know that this is equals to the ratio, which will be our P1 we have, it's 90, times the ratio, it's 8.6, raised to the index, which is 1.3. And our P2, we get that it is equals to, we'll put it here, 1476.014. I didn't put it in the diagonal. 1476.014 kilopascal. That's the value of P2. And then we go to calculate for the value of P4. We are going to use the information between point 3 and point 4, which will be P3 V3, and it's equals to P4 V4 raised to n. We are looking for P4, we make it the subject of the formula, which will give us P3 times V3 divided by V4 raised to n. And we know that this P3 is equals to P, we know that V3 is equals to V2 and V1 is equals to V4. The ratio is equals to V1 minus negative divided by V2. This is equals to V4. This is equals to V3. But here we are having not V4 divided by V3, but V3 divided by V4. Therefore, this will be equals to V3 is equals to V4. And we are going to say our P3 is 4,400 times the ratio, it's 8.6 raised to n, which is 1.3. And we get that our P4, it's equals to 268.29. That's the value of our P4. And we go to the next question, which is question number D. They say calculate a work done per cycle. And for work done, we are going to use the formula that says work done is equals to, mean effective pressure is equals to work done times the mass of the gas per cycle divided by the swept volume. We are not going to use that other formula because we do not have the gas constant, which is R, and we do not have mass, therefore we cannot calculate for the gas constant. So here we are going to substitute 700, the work done, divided by the swept volume. Swept volume, this is our swept volume. We have to convert it to meters, meter cube, sorry. It's going to be 4283 times 10 to the power negative 4. and we are not given the mass. Therefore, we are going to put 1 and calculate for the work done per cycle per unit mass. The work done that we are going to calculate here is per unit mass. Therefore, we are going to get our work done as equals to 300. It will be 0.3 kilojoules, and we convert it to be 300 joules per cycle per unit mass, because we used 1. We are not given the mass, and we are also not given the gas constant. We have to put the mass here. Therefore, we put 1 to calculate the work done in joules per cycle per unit mass. And then from here we go to the next question, where they say calculate the temperature at all the main points in the cycle if the temperature at the beginning of the compression is 350. It's given information. Let's put it in black. 350. We will erase this. It's question number E. We are looking for temperature number 2, number 3, and number 4. We are going to use the information between 1 and 2 to get temperature number 1. And the formula that I chose is P3 divided by T is T2 divided by T1. It's equals to V1 divided by V2 n raised to 1. And T2, it's equals to T1 times V1 divided by V2 raised to the index minus 1. T1 is equals to 350 times this as the ratio, index minus 1, which will give us T2 as 667.448 kilopascal. From here, we are going to use to calculate for T3 using 0.2 and 0.3. We know it's constant volume. Therefore, we use P2V2 divided by T2. It's equals to P3V3 divided by T3. It's constant volume. Therefore, this one cancels out. T3, it's given by T2 times P3 divided by P3, sorry, by P2, which will be our T2 667.448 times our P3, which is 4,400, and P2, it's 1476.014, which will give us our T3 as 1989.664 kilopascal. And then from here we are going to calculate our T4. T4, we'll use T4 divided by T3. It's equals to V3 divided by V4 raised to the index minus 1. And then T4 is equals to T3, which is 1989.664. V3 minus V1. This we know it's equals to V2 V1, which is equals to inverse of the ratio. And we are going to say 1 divided by the ratio raised to the index minus 1, which will give us a temperature of 1043.350, and that's our value of T4. And it's the end of our question. I will see you on the next lesson.